something. That's great. Okay. All right. So hi everyone again. So I'm Tansu Daylan. I'm a new assistant professor here in the Department of Physics, and it's awesome to see this crowd here, motivated to hear more about the solar eclipse and the broader topics that I'd like to cover today. In fact, most of our discussion today will not be directly based on the solar eclipse, because we had a series and the previous talks actually covered various aspects of the solar eclipse already. My goal today is to actually cover other interesting aspects of what we call syzygies, and solar eclipses essentially happen to be one type of such alignments in the universe that we can study. In particular, I will be talking about planets beyond our solar system, but we will contextualize that within the context of solar eclipses and these alignments. I will try to leave enough time towards the end, maybe at least 15 to 20 minutes, we'll see. Depending on the questions, I guess, during the talk, feel free to ask questions. If there's a pressing question that you feel like might be useful to address during the talk, please do shout out. We can make this as interactive as possible. Otherwise, I'll try to leave also time for questions at the very end. And yeah, so this will be about an hour session focused on solar eclipse and the broader context of syzygies. As I mentioned, I'm new here and still exploring. On the left, I put a picture of our lovely campus, Stanford campus. And one of the nice things about our campus is that it has a major axis, which means that you can actually look for alignments with that axis. And this is actually a photograph I took in the fall semester, where our main axis actually aligns with the rise of our sun in the morning. So that's what I'd like to call a Washoe-Henge, in analogy with Stonehenge, similar idea. So what we will not talk about today is, first of all, again, the history and the elementary physics of solar eclipses, which have been covered before. And in case you are wondering, we will also not cover how alignment of planets and stars may affect your life, including how frustrated you may be at the moment. And I highly encourage you to look for other reasons for such events. We will talk about the information content of transits and also eclipses. I will define them more rigorously moving on, of stars and planets. And we will also talk about how we use these transits and eclipses to characterize planets beyond our solar system. And from now on, I will refer to them as exoplanets. So first, some nomenclature to basically be able to go over this material. When two objects on the celestial sphere basically get close to each other, you may have heard about the term conjunction, maybe not so pulse, but basically when they, any two objects on the celestial sphere get close to each other and are aligned either along what we call the right ascension, which is like the horizontal component of the equatorial coordinate system we can position at the center of the Earth, or basically along the ecliptic longitude, then we call that a conjunction. It's kind of a loose term, but usually you pick a coordinate axis and say if the two objects are kind of aligned along that axis, you call it a conjunction. Like you can think of, for example, the conjunction of Jupiter and Saturn, or whatever, two planets along the ecliptic, for example. And a pulse is basically a more refined term. If the distance between two objects is minimized, then we call it a pulse. It comes from a pulsus, from Latin. Basically, it just means to kind of come together. And when the two objects actually coincide along our line of sight, we call that a syzygy. Comes from, I believe, Greek, Old Greek, syzygia. And this basically is not just a minimization, but actually an alignment, please.
What is the difference? I don't see the difference between a conjunction and a syzygy.
So a conjunction does not necessarily require line of sight alignment. So if, for example, two objects get close to each other and have the same for example, a close position and say the same right ascension, it's still called conjunction.
Oh, okay.
No.
Oh.
Okay, so now we will focus on syzygies. I'd like to make the case that syzygies are unlikely events. Unlikely does not mean that they don't happen. We will come to that. But planets and stars are small objects. First, let's establish this fact. In fact, planets are much smaller than stars in general. There are some cases we will cover if you have time, but usually stars are much larger than planets, which means that the relevant spatial size you should have in mind is that of a star. Now, the interstellar distances, or in fact, even just the distances between stars and planets, are actually much larger than the typical sizes of stars. A couple of numbers here. First of all, a good number to keep in mind is that our Earth is much smaller than our sun, about 1 to 100. But even beyond that, the separation between typical stars is order parsec, and a parsec is just about 3 light years. And 1 parsec is about 200,000 times larger than the distance between the Earth and the sun, which we call the astronomical unit. And that astronomical unit itself is about 215 times that of the radius of the sun. So these are much larger numbers compared to the radius of the star, or I guess our sun. So when you think about it, these are almost like points in a vast space. So for them to actually align along any line of sight, choose a random observer is very small. There are certain situations where this actually can be realized. In fact, I mean, they get realized regularly. That's when you pick an observer reference frame. So for example, this is shown with the gray here. And the orbit of some object is basically shown with the yellow or plane here. If the reference direction is aligned with the so-called node of the orbit, then there's some alignment that is temporary that we call a syzygy. Now, when I provide examples, this will be more clear. So first of all, I'd like to start with the solar system. So for the solar system, we actually have 2 objects that can align with our line of sight to the sun, in addition to the moon, which we have covered again in previous lectures, so I will not go over that. They do actually occasionally occur, both for transiting planets, which I will cover later on, but also for the inner planets of our solar system. Mercury does this, in fact, very often, about 13 to 14 times per century on average. We are talking about gravity and nonlinear dynamics here, so nothing is exactly periodic and nothing is exactly the same over time, but it kind of fluctuates. But the case of Venus is even more interesting because Venus transits are actually pretty rare. They have a quasi-periodicity with a period of about 243 years, much longer than our human timescales. And this makes it kind of interesting. The very first such transit was observed, in fact, based on some very ambitious work of 2 very young British astronomers at the time, who actually redid the calculations of Kepler and predicted that the 1639 transit would actually occur, and went on and actually observed it, which was a very, very important time in the history of astronomy. So very early on, right after 20, 30 years after Kepler put forward his planetary motion, model of planetary motion, which essentially rewrote the entire planetary model as we understand it, because back then it was first circular from the times of ancient astronomy, such as Ptolemy, but Kepler basically introduced the eccentric orbit, then basically started predicting the transit times of the inner planets. But that he made a slight mistake. In the Rudolphine tables that he published, there was a little inaccuracies, and basically these 2 astronomers redid the calculations and observed it in 1639. Since then, we had 3 other pairs. These pairs are separated by 8 years, so there are 2 transits separated by 8 years. Each of which is separated by something like 121.5 years right now. Again, this like 1,000 years later, it will look different. 1,000 years before, it was different because of the nonlinearity of gravity. But basically, this is how it looks. You see Venus just like a black circle on the stellar surface. This is from STO, which is a NASA probe looking towards the sun. And in 2012, the very last transit of Venus that we could plausibly observe, because the next one is 2117. Regardless of how much broccoli you eat, I don't think we'll be around back then. But I think this is kind of spectacular that there was this rare event, in fact, pair of events, and they were observed very extensively. And I was actually, back 2012, I was taking finals. Back then, I was an undergraduate student, but I still remember how important that event was. So we will now switch gears, and I'd like to, before kind of I lose all of you, I'd like to just spend just a little time talking about the fundamentals, ab initio principles of how we do this science. So I will be showing some equations. Please don't get scared. It will not be very fundamental to the discussion, but for the mathematically oriented people, I'd like to be also comprehensive. So this is the geometry we are talking about when there's a transit. So you have some stellar disk, some star with radius RS, some planet with radius RP, and then we define so-called the impact factor, which is the A, which is the semi-edge major axis, which in more simple terms is the distance between your star and the planet, times the cosine of the inclination angle. So this A times cosine is a very important parameter here, the impact parameter, B, and that will essentially lead to a few important definitions here. The details are not important, but I'd like to actually send across a few important physical intuitions here. First, the transit probability is the sum. I will come to that plus or minus sign very soon. The sum of the two radii divided by the distance between the two objects. That is the transit probability. Now, in general, the reason why that's the case is because an arbitrary observer will have a cosine I distributed randomly between 0 and 1. Hence, P sub TR, which is the transit probability, becomes this object. Now, why there is a plus or minus is because if it's plus, it means it can be any transit, including grazing transits. Whereas if it's a minus, it needs to be such that the planet is actually transiting within this solar disk or stellar disk in general. The second one, and by the way, this probability is very small. Again, because of the reasons I mentioned, if you just contextualize what I said a few minutes ago, this is a very small probability. Now, second row, transit depth. This is kind of a technical word, so I'd like to expand it. First of all, think of the star as a bright object, as they are. So there's certain luminosity per unit time. There's a number of photons raining on you per unit time. We call it luminosity. And basically, the idea is that this object with radius r sub p is opaque. So it's occulting the photons that would otherwise be raining down on your telescope or your eyes. So that is actually reducing the total number of luminosity that you get from this bright object. And it is reducing it by a factor that is equal to D. That is the ratio between the radius of the planet divided by the radius of the star squared. Now, the square is easy to understand because we are talking about the ratios of the areas, and area is pi r squared. So that basically creates the square there. And the third one is transit duration. I will not verbally derive this because this is part of my actually a course that I give. So there's some math behind it. But basically, the idea is that the difference between that cosine term and that r summation divided by a term essentially sets how long of a transit you will actually observe. If it's grazing, it will be very short. If it's equatorial, it will be long. So based on the transit duration, you can actually infer the inclination if you know your star. I will skip some of the details, but if you can characterize your star, if you know its radius, if you know its mass, then there's some density term in there, again, skipping that part. But eventually it means a measurement of the transit duration actually makes you sensitive to a measurement of the inclination. And most importantly, which I kind of skipped, but I hope now you can see that if you actually measure D, the transit depth, it will, and knowing to some uncertainty the radius of the star, it will allow you to measure the radius of the planet, which is very important. And by the way, as a reminder, these transits are periodic, or at least quasi-periodic, which means that you can repeat this measurement over multiple transits, and then measure one other very important quantity, which is the orbital period. So you have the orbital period, the radius of the planet, and also the inclination, which are all inferable in principle from transit photometry. This basically forms the basis of the transit exoplanet science. And these are kind of the most important observables that we search in what I will now refer to as time series photometry. I know this sounds like jargon, it probably is. It just means that you take a star and you measure its brightness over time. And by brightness, I mean, in astro, there are two main measurements, I guess, you can make. There's photometric, which means brightness, and astrometric, which is position. So you take a star, measure its brightness over time, and that gives you a data set over which you can try to infer these properties.
Why is it important that you know the transit probability? I mean, either it happens or it doesn't. You either observe it or you don't.
Awesome. We need a very detailed understanding of transit probability, because when we find transits and characterize them, we ask the question, well, okay, I say observed 10 transiting planets out of, say, 1,000 stars. What is the underlying occurrence rate of these planets? So you have to do the reverse problem. Based on some measurement of transits, you have to go back and actually address the much more scientifically interesting question of what is the underlying occurrence rate. In order to get to that step, you need to have a really good understanding of your so-called selection bias, which the transit probability characterizes. Okay, so sorry for a few Turkish words here. I did not have the time to update this, but basically the idea here is that you have the stellar disk. So this is essentially some arbitrary star, and you on the lower. This is an animation, by the way. So the planet started crossing now the stellar disk, and you have the light curve going down. So you can imagine certain y-axis value as a reference value, and the curve is now drawing the total luminosity of the system as a function of time as the planet transits its disk. One thing that you probably saw, but I just want to highlight that, is the brightness is not homogeneous across the stellar disk. We call that the stellar limb darkening. It was first discovered in our star, but then it can be generalized to many other stars. In general, higher mass stars manifest a stronger limb darkening. Lower mass stars are typically very red and more homogeneous across their stellar surfaces. And then you complete that U. And basically, this is how we actually forward model. We take our star, we collect the expected number of photons, especially, I mean, there are ways to do this analytically as well, but when you have phase curves, multiple planets transiting, there are stellar spots that you need to consider, and non-spheric geometries. So in order to account all of these, we usually do these photodynamical models. Bringing all of this together, I just want to give you the big picture now. So given a transit light curve, you are sensitive to the depth of the transit, again, RP divided by RS squared, which is the area ratio. Then you are sensitive to the transit duration, and the transit duration, given the stellar properties, allows you to infer the inclination. Then you also measure your orbital period based on the periodicity of these transits. Now, what do we do with these? Oh, maybe forgot a couple of other things just to highlight. Again, not basis material, but This is basically showing you how the transit depth changes if you change the radius of the planet. This is now showing you how the transit shape changes when you change the so-called the amount of limb darkening. Green here is the one with the least amount of limb darkening. And this actually depends on the band with which you make the measurement. And now this is showing the effect of changing the inclination, the orbital inclination. As you can see, the cosine I is a very small number. So inclination is actually a value around 90 degrees. So that means you take that reference plane, you rotate it by 90 degrees. So because the reference plane of an observer is actually has the normal vector aligned with the orbital vector of the planet. So that's why we need to rotate it by 90 degrees. For transiting systems, obviously. I mean, otherwise, for example, if I is not around 90, it will not be a transiting system. This is a more general, I guess, aesthetically pleasing view of the same idea as a function of time. The photometric modulation tells you the depth, hence the radius of the planet. And if the radii are different, the depths are going to be different. And notice that here, the occulters have this different radii, but the stars are the same. Sometimes it's the occulter that can have the same radius, but the underlying stars, the host stars can have different radii. Okay, so now some little history. So given this, people expected to basically be able to discover exoplanets using this method, and they tried for a long time. In fact, I mean, I'm a history nerd, so I basically keep reading about the history, and the history really takes you to almost like 19th century when people actually very realistically tried to do this, but it failed. And the reason why it failed so many times is because using photometric methods, people had these plates that they were trying to measure the brightness from, but you don't have the photometric precision. That is, the uncertainty on your measurements is too much. You make too much of an error when you're trying to measure the brightness in order for you to be able to resolve such photometric brightnesses. For example, let's take this. This is the plot from the very first paper that discovered the very first transiting exoplanet from 1999. And you can see that the relative brightness drop is about 1 to 2%. So you need your photometric measurement capability to be producing error bars that are much smaller than this. Hence, that was not within the capability, but of searchers. But there are other reasons as well. I mean, apart from the fact that we started using so-called charged coupled devices, which are much more sensitive to few photons. You can basically, using photoelectric effect, take one photon and then amplify it and be able to do precision photometry with very few photons. Basically, that's the idea with CCDs. But even before then, there's also the idea that transiting searches fail because, going back to my previous point, transits are inherently rare phenomena. So you have to be actually doing this search over many stars before you randomly hit one where the planet happens to have a cosine I close to 0, so that you can actually play this game. Now, this 1999 detection might actually click for at least some of you who might know about the exoplanet research history. This is not the first exoplanet discovered, for good reasons. For the reason I just mentioned, the very first discovery actually came from a completely unknown method that I will not even discuss. Pulsars are a very different type of stars, and they use timing of pulses from dead neutron stars to figure out that there are some planets around them. But then a few years later, this was back in 1992, a few years later, the very first so-called radio velocity detection was achieved. 1995 was the first paper for a planet around a sun-like star to be discovered, or at least confirmed. There were other candidates before that, but the very first confirmed exoplanet that came out of radial velocity method was 1995. And then they basically started using the radial velocity detected exoplanets as targets for such surveys. That increased their detection probability because you now know that there's just a planet around it. You're just basically searching for a planet that actually transits, which increases your probability of success. And the first successful detection again came towards the end, the fall of 1999. Very rich, interesting history there. So we now fast forward to TESS. So TESS is basically my baby because as postdoc, I worked on TESS and have been since working on TESS for 6 years-ish now by now. And TESS stands for Transiting Exoplanet Survey Satellite. This is TESS, got 4 cameras, bunch of solar panels. It's a small mission. Well, I mean, small as in actually in NASA standards, it's a mid-X, middle size, but it's not like Hubble. You know, when I talk to public, I just want to make sure I give the right amount of scale. It's like $200 million, excluding launch costs. So it's not as expensive of Hubble or JWST for that matter, but it's space-based. And basically it was launched into space in 2018 during the week that I was actually defending my thesis. And then I started working on TESS as a postdoc right after my graduation. It's a full sky survey. So as you can see, it got 4 cameras, and the cameras are pointing to different points on the sky. And it basically looks for such transits, as I mentioned. These are alignments that are intrinsically rare probability, but TESS can find these because it's actually doing this experiment over many hundreds of thousands of stars at the same time. This is enabled by the fact that the cameras actually are wide angle, and this allows you to do photometry at the same time over many hundreds and thousands of stars. That number can actually depends on how faint you want to go. So you might, in the literature, find different numbers, and that's okay, because it basically depends on where you cut in terms of brightness. Fainter stars are interesting, but they're not as useful for finding these because your photometric precision degrades. Please.
I think it's far easier to space on the ground, right?
Yes, that's right. From ground, there's also the day, which is issue, because the transit duration is usually a few hours. And you want to be able to measure the so-called ingress as well as egress, and some measurement before ingress, before the transit, and sometime after the transit. Usually that is not easy to fit within a night, especially if you are kind of in the summer season. But in general, I mean, doing transit photometry, full transit photometry from the ground is not easy.
Is the atmosphere a big factor?
That is indeed a big factor, which I will come to. Yes, the photometric precision you can get from the ground is basically degraded due to the fact that these stars are point sources, and you're basically there's the notion of atmospheric scintillation because they're roughly point particles. They scintillate in the atmosphere, and due to the space and time variable atmospheric refraction, the photometric precision you get is basically degraded. So the brightness, the apparent brightness of a star kind of fluctuates over time at percent level or sub-percent usually. And again, if you can find hot Jupiters that happen to be really large, then you can still discover them. Yeah, so this is basically the orbit of TESS. It's in cislunar orbit. It's around the Earth, but not, low Earth orbit, for example. It's not very close to the Earth. It's kind of in the middle way between Earth and the Moon. And it's in a very special orbit that is in resonance, mean motion resonance, 2-to-1 resonance with the Moon, so that actually keeps the Earth it keeps the machine, the instrument in a dynamically stable or quasi-stable state. So otherwise, if you send something to cislunar orbit, you have to be very careful because the moon is perturbing your instrument dynamically, gravitationally all the time. So it can actually cause it to lose dynamical stability very easily. But the choice of the orbit basically precludes that. Now, TESS, as I mentioned, is a full sky survey. So it basically pivots around one of its cameras. And then it started with the southern sky, then with the northern sky, not exactly in this way. There were a few perturbations that had to be introduced due to the existence of our lovely moon. But apart from that, this is basically the type of data we get. This is looking towards the southern ecliptic pole. And that's maybe, does anyone recognize what this is? Yes, so the giant Magellanic Clouds. Here, let's see. This one, is this the correct one? Yeah, so this is the more up-to-date version. So you see there is basically a like what we call garage door in the northern plane, northern ecliptic hemisphere. And it's, again, as I said, moon is kind of in the view, and we want to avoid, well, first of all, TESS is always anti-sun, so it's pointing away from the sun, but you're in cislunar orbit, and when you point away from the sun, the Earth and the moon can come into view, and that basically causes some scattered light. Okay, so with TESS, what we are trying to do is to find small planets, and to find small planets, you need high photometric precision, as I mentioned. And TESS is basically being able to do this because it can go faint. And when you go faint, you're actually now you're more sensitive to small stars. And those small stars actually produce a higher transit depth, because at fixed occulter radius, if you reduce your stellar size, then it becomes it produces a higher transit depth. And we actually use this to find planets around small stars. So by small stars, I mean the relatively cooler M dwarfs. So that has been one of our excitement in the mission, although sun-like stars are also very important. So this basically plot shows the cumulative number of exoplanet discoveries over roughly the last 2 to 3 decades. And you can see there, do you see my, yeah, here we go. So there are 2 discontinuities here. These are the Kepler, basically Kepler published a few, but when I say Kepler, I mean the Kepler, the space telescope. Basically, our colleagues back then published a few papers here that confirmed a batch of hundreds of exoplanets at the same time. So that kept up with this, what we could potentially call the exoplanet Moore's law. But now, in the last few years, that's no longer the case, and it's the increase is much more, I guess, smaller, much smaller. And we kind of expected that, because TESS is not supposed to be finding many exoplanets. It's supposed to be finding small planets that are amenable to further characterization. That's the goal of TESS, and that's been already achieved, because the level 1 science requirement of TESS was to find 50 small exoplanets. By small, I mean smaller than Neptune, so 4 times the Earth radius, that were able to be characterized in a sense that their masses would be able to be measured. And that's already accomplished. In fact, that was accomplished a few years into the mission. So here you see the photometric precision. I won't really define what this object is. It's kind of, first of all, one thing to note, this is log, but then this is magnitude. And magnitude is logarithm of the brightness. In fact, it's the inverse logarithm of brightness. So to the left, you have brighter objects. To the right, you have fainter objects. And this is log. So because of that, you can see that there's some saturation here of the noise that you get. And this is actually in units of parts per million. We use that a lot, ppm, parts per million. And you can see that towards the fainter stars, our noise is increasing. And I won't really go into the physics of that, otherwise I won't be able to finish this on time. So here you see the number of exoplanet discoveries that Kepler achieved and TESS achieved. So obviously Kepler dominates in that era. But those with precise masses, TESS is doing relatively a better job. And this actually plot is a plot that I made maybe a year or two ago. So this probably is the blue part is in fact increasing as time goes by. So yeah, this cuts at 2022. Our detections are continuing with an accelerated rate. And one thing to note that TESS actually makes these discoveries of exoplanets that are relatively more nearby. There's a reason for that. TESS has a much wider field of view compared to Kepler. So Kepler had a small field of view that it was able to integrate for a longer time so that it could go fainter in its searches, whereas TESS is full sky, nearly full sky. So it's not per area going as deep as Kepler. So it's essentially more sensitive to brighter stars as compared to Kepler, but brighter stars in a more generic sense, in the sense that, for example, we are more sensitive to open clusters where you can find young systems because there's a higher diversity of the stellar population when you look at the entire sky. That's the main advantage. Now, a couple of takeaway points about the exoplanet detections. Now, this talk is about, again, going back transits. And one thing I'd like to highlight is that transits in the exoplanet sense give you a few important messages in the field. Some nomenclatures, usually this is the plane of the planetary radius on the y-axis and orbital period on the x-axis. As I mentioned, both of these are things you can infer from a transit based on the transit depth and recurrent nature of the transits. Then you have the Jupiter-like planets up there. You have the so-called sub-Neptunes. They do not exist in our solar system, which makes them very exciting, interesting. And then we have the terrestrials, the small ones. So if we basically put that on the right, and now on the x-axis, I just changed the definition just a little. Instead of orbital period, I'm plotting here so-called irradiation, normalized to that Earth receives from the sun, the 1.4 kilowatts per meter. So that's important. So 1.4, but that kind of is top of the atmosphere value, I think. But anyways, it's over that. So you normalize it by that, and you get basically a distribution that looks like this. Now, if we focus on the small exoplanets, which I will now highlight here, and zoom in that area, you'll see basically some underdensity of points to the left. And that's one thing you should expect because of the transit probability. I want to highlight that because the transit probability is so low going to the left, we have an underlying, we have a lot of planets, but we are not detecting them. So we have a strong selection bias against going to the left on this plot. So instead, we go to the right. That's what we do. We are trying to make sense out of things we can actually measure. So far, this part of this plot has been explored much more in detail because we are more sensitive to them, especially on the right-hand side. These are really close in, so very easy to find around stars. And one thing you might see is that there's actually a demographic feature here. We call that the radius installation valley. It's one of the most important findings of exoplanet research. Trying to make sense out of this radius valley, how and why that's produced is a very important scientific objective of the field at this point. There are many telescopes being produced, many scientific collaborations generated because of this problem. And I really won't go into the physics of this, but we have models that can actually produce this, but I will skip it for this audience. And we also go deeper than the brighter kind of objects where we can do the detailed characterization. This has been one of our ongoing tasks to actually extend the search to fainter magnitudes and has been keeping me busy for the last few years. I want to actually leave time for questions, so probably I will not finish everything, and that's totally fine. There's a few things I'd like to actually talk about at the very end about the solar eclipse itself. So I should probably wrap up very soon. So we ask a lot of questions in the exoplanet research field, ignited by the transiting exoplanets that I described. Such questions, why Mars lost its atmosphere. There's atmospheric loss is related because in order to actually infer this problem, first we need to measure the radii of the transiting objects, and then do that as a function of energy or wavelength. And that's a very important problem that I will very shortly touch upon very soon. This is one of our highlight detections from the TESS mission. Andrew and I worked on this a while ago, and the idea is that you have now a white dwarf, a very small star. White dwarfs are as small as our Earth, but then you have a giant planet about Jupiter size that's actually transiting it. So the transit probabilities are very different in that system, obviously. Now, the interesting thing is that we really don't expect such planets to exist because white dwarf is an evolved star. A white dwarf probably did something really messy before it actually became a white dwarf. It shed its outer layers to the interstellar space. It lost mass, and in doing so, it really disturbs the planetary architecture around it, we think. So something interesting must have happened for this planet to actually exist. It's one of the so-called impossible planets. But certainly it exists, so we need to explain why. I will actually skip 1233 because I just don't have time. Let's skip all of these. I want to come to one thing about JWST that, this is JWST, in case you have not seen it, but I'm sure everyone did. So this is a 6.5 meter mirror big telescope, $10 billion, kind of the most expensive it gets style mission, and it certainly does exoplanet science. We have been very fortunate to be able to use JWST since its launch, and I personally was very excited because very recently my team was awarded more time on JWST, so we are all very excited about it. But basically, this is the focal plane of JWST, so it has multiple detectors that it can use to record the photons that it collects through this optical path that you're seeing. Again, too much to actually talk about very exciting stuff, so I will need to refine it to just one discovery we did using essentially transit method, but now this time across wavelengths. So the idea is you do the same. You watch your star as you watch your planet. Well, you actually watch your star. That's actually right, because the planet is not bright. So you watch your star as the planet transits, and you basically collect photons in buckets of wavelengths. Okay, so you do that multiple times. Well, you transit, obviously the transit happens once, so you need a clever optical path that can actually send different wavelengths into different buckets. We call that spectroscopy. So this is what you see on the vertical axis. So you measure your transit across different wavelengths, and you find this. See here, different wavelengths have different depths, and this basically pointed to a very important finding, a major finding in the field, the very first detection of carbon dioxide in the atmosphere of an exoplanet. So this was something our larger team basically published last year. And it's one of the major results of the exoplanet research so far. I mean, apart from, I guess, maybe the very first detection of exoplanets with each method, this is one of the major accomplishments of the field in that now we are able to use JWST to measure the atmospheric properties that are available at much longer wavelengths than was possible with Hubble Space Telescope. Hubble Space Telescope had to start at about 1.5 microns. Here, if you look at the x-axis, you see 3, 4, 5, etc. So this is far into the infrared. Whereas with Hubble Space Telescope, which we all love, I mean, it's a very important telescope, but with Hubble, we have not been able to do this type of science.
What frequency would be the nitrogen and oxygen?
So yeah, oxygen is very hard. So we instead look at ozone, but they're actually in the optical. So technically you could, I think I have a plot of that somewhere here. Technically, so you, oh, this is actually, yeah, only showing the ozone as a band, but there are actually refined details there. But basically that's, you can, something you can actually search in the optical. But Hubble Space Telescope also suffers from a much smaller aperture. It's not like the 6.5 meter JWST aperture, so it's not as sensitive. So we need for that a telescope that has a much larger aperture and also can observe in shorter wavelengths. And we are very excited about the Habitable Worlds Observatory, which I hope I will at some point in my life see fly, but unfortunately not anytime soon. But the survey from our field as the astronomical research field in 2020 basically came out suggesting that we build a major telescope that's going to have roughly the aperture size of JWST, but also be able to do many other things. And we now call that the Habitable Worlds Observatory. And the idea is for it to fly in the early 2040s. Okay, I should definitely wrap up very soon. So with this, I'm just going to switch to just the solar eclipse bit, and then I will take questions. So that's the plot. Yeah. Okay, so maybe just one point. Basically, I'm the contact person for WashU for Astronomical Society, American Astronomical Society. So if you have any questions, if you want to get involved in any component that's in any component of astronomy, please reach out. This could be in the form of volunteering, helping out with advocacy policymaking, or just get involved in citizen science, anything really related to astro. There are ways, and in fact, AAS supports the field in any along many axes, such as supporting open access journals and meetings and various other things. So please reach out if you're interested. And here comes the solar eclipse. So we are approaching April 8th, and the solar eclipse, which is basically a transit of the moon across a solar disk, it's going to be happening about 2 p.m. local time. And definitely share the experience. It's definitely, I mean, as a scientist, I feel like it's a unique connection between our planet, our host star, and our natural satellite that we call the moon. In fact, working on exoplanets, I mean, we work with the transit data all the time, but when you see it kind of in a local experiment, that's very exciting. And as an Earthling, certainly it's just the fact that it kind of gets cooler for like 3 to 4 minutes, and you suddenly see like signs of nightlife, I guess, around it. It's definitely a great experience. So whatever you need to do, if you need to travel a few hours to the south, I definitely suggest you do that. It's worth it. Now, on top of that, some safety. Please do not watch the sun with your own naked eyes. One, I guess, worst thing you could do is try to watch the sun with a binocular or something like that. Don't do that, please. You should, in fact, be using eclipse viewing glass. We have many of them here. So as you leave, if you're planning to attend any of the events, please take one and take it to your children or whatever. If you're going to be doing like a group activity around that day. One thing I can say is that it will not be the totality, what we call the moon totally occulting the sun, will not be visible from the St. Louis region. So you should drive down about an hour and 2. So not a big trip. You can just do that, I guess, anytime that day. And it will be worth it. Well, first of all, we need good weather. Obviously, we will be crossing our fingers for that. But on top of that, a bunch of our faculty will be actually traveling down to the Bollinger Mill to give a few talks and actually participate in a public event in collaboration with the state park, and that should also be very exciting. So if any of you have any questions about that, happy to answer. And certainly we live at a part of continental US where the cloud coverage can be potentially higher. So we're crossing our fingers for that. The next best option is to certainly be, on a plane or something. There's going to be a Southwest Airlines, I guess, flight that's been, probably sold out. But on top of that, you could just maybe join if you have a pilot friend or something, you can rent a small airplane and actually guarantee your spot. But, then the airplane can break or something, and there's always some ifs. But okay, with that, any questions? So I will stop it there. Thanks for joining us. Yes, please.
If we stay in St. Louis area, what percentage of the eclipse will we observe?
So from the St. Louis area, it will actually be what we call partial eclipse. So it's only going to get slightly fainter, but it will not be a spectacular experience. So if you are in the St. Louis region, I definitely encourage you to just take a trip a few hours south and actually experience totality.
Thank you.
You talked about the radius valley earlier with the graph,
Mhm.
how important it was. What actually is the radius?
So radius value is a so-called demographic feature. So I need to expand that. Demographic feature means you take your exoplanets that you've discovered, you undo the selection effects. That's the key part. So it's not just the raw data that you discovered. You undo your selection effects. Then you look at the distribution. You basically, per area in your plot, you measure how many planets per, radius, per insolation do I get? And that draws you a contour, say, along a two-dimensional plot. And basically, if you do this for the radius, planetary radius versus irradiation that they receive, there's essentially a underpopulated, not a gap, but a valley. So there are planets there that we predict. It's not like no planet is allowed to have that radius or insolation. It's more that it's more relatively unlikely. And we are trying to understand why. There are many models, but again, I don't think this audience is interested in the details, but if you are, just let me know.
So essentially, there's no mid-sized planet, less mid-sized planets.
Okay, by mid-size,
or the Earth size and then Jupiter size, but in between there's much less.
okay, I think we need to be a little more refined here. So by mid, I'm specifically referring to about 1.8 times the Earth radius. And that actually depends on the radius as well as insolation. It's like there's a slope there. So for highly irradiated planets, the valley goes to higher radii, just slightly, 2.0. And for lower insolation, it goes the other way around. But we are talking about a distinction between what we refer to as super Earths and sub-Neptunes. So the value is in between the super Earths and the sub-Neptunes. In fact, the sub-Neptunes, if you take into account the selection bias, is, we think, a very common outcome of planet formation.
I have kind of a trivial question. I got the impression that most of these exoplanets are in elliptical orbits around their stars. Why aren't they circular?
Okay, so in general, any orbit in the universe, if you just do the math from first principles, is elliptical. So there is no circular orbit that is like what Greeks got fascinated about. There's no ideal circular orbit. All orbits are essentially elliptical in nature. Now, if you make, say, a plot of the distribution of ellipticities, you certainly get a cluster around circulars. I mean, there is some maybe residual eccentricity to all orbits, but most of them are close to circular. And there's a reason, because when an orbit is or somehow due to some resonance becomes elliptical, there are ways dynamically to excite eccentricity naturally. But after that, there is also natural ways with which eventually orbits become circularized, especially through tidal effects and body interactions. So when some eccentricity is excited in nature, nature eventually, most of the time, not always, finds a way basically to reduce that eccentricity. Again, there are many highly eccentric planets in the universe, and that's when such processes are inefficient or have timescales that are much longer than the relevant timescales.
How do you distinguish a planet from a red or a brown dwarf?
Sorry, how do you?
Distinguish if it's a planet versus a red or brown dwarf.
Ah. Okay, so a brown dwarf would have brightness in the infrared, whereas a planet would still, but at much lower pressures. At much lower intensity. So the what distinguishes a brown dwarf from a planet, by the way, is not its luminosity, but its mass. But observationally, it's hard because we don't directly measure the mass. Usually, we just measure how bright it is across wavelengths. So we try to distinguish it based on the infrared excess.
So you're doing spectral while you're doing this too, besides just.
Yeah.
Oh, you are?
Yeah, I mean, whenever we can.
You're not just doing photons, you're doing extra, okay?
Yeah, whenever we have the telescope resources, which is rare, yes, we also want to get the infrared spectrum.
You were talking about all the different physical properties you can infer from a planet transiting the stars. It doesn't have the intrinsic luminosity.
Mhm.
Can you infer the same kinds of properties when you have a binary star system
Mhm.
that are transiting each other?
Yeah, a binary star system, or if they're eclipsing, we call them eclipsing binaries, they obey the same laws of nature. So the exact same mathematical treatment is valid for such systems. In fact, usually there are backgrounds for us. When we see a transit, it's much more likely for it to be coming from an eclipsing binary as opposed to a planetary transit. So we have to actually do a few tests before we can convince ourselves that we see small-sized objects, that's also known as a planet, not an eclipsing binary that is otherwise so-called diluted due to some third object that's luminous. So usually eclipsing binaries would create a transit depth that's inconsistent with a planetary transit. But if there's a third object that's unocculted and producing light, it will actually so-called dilute your transit. And when your transit is diluted, you can mistake it. You can just think that it's planetary, but actually it's just an eclipsing binary.
Your test project, are you in partnership with other countries?
TESS is NASA funded, so but the data is public universally. So basically, TESS data is being used by many international colleagues to do great stuff, but the operations, the main pipeline that runs, that's in the US. But the data is served internationally and the science is shared internationally.
And what would be the basic commercial use of the information you're learning?
Commercial. Well, as a natural scientist, I don't think about that, but I'm pretty sure there are ways to do that. But one thing to keep in mind is like this is taxpayer money funded mission. So doing commercial work on it might have some boundaries, but I just don't know, have never thought about that aspect.
So I understand now that you have telescopes. Are there planets that can't hear the question?
I will repeat.
Are there planets that you found oxygen or methane or carbon dioxide or things, water in the atmosphere where you think that might be a habitable planet?
Right, let me repeat the question. So the question is, JWST started characterizing exoplanets. So are we finding, the relevant biosignatures? Quick side note, even before JWST, we actually had the capability to measure and characterize exoplanet atmospheres. That's not new. The new part is the fact that we are able to do this in infrared and in particular mid-infrared. That's completely uncharted territory. And there's a lot of degeneracies we can break in our modeling of exoplanet transits and I guess in general atmospheres. Than we can only do in optical. Now, having said that, yes, we are certainly in a much better position with the capability of infrared to be able to find, for example, what you refer to as carbon dioxide, methane, water. Water is also, by the way, accessible in optical or near infrared. So it was accessible to HST, but methane wasn't. Carbon dioxide wasn't. And so far, we as in the community, I have been involved in many projects, but in general, when I talk about this, I'm generalizing the concept. The field has found or not found these signatures in various exoplanets. So right now, there's a lot of data leaking into the field, but no robust conclusions because this is very much in flux. We are trying to make sense out of the surveys we are conducting, but the process of going from measurements and no detections to actually complete and trustable atmospheric models is a step we are yet to take. Now, you asked about something that's even a step further than that, because actually having an atmospheric model doesn't necessarily mean that it's a biosignature. For example, if you find methane, methane itself is not a biosignature. It's not indicative of life. Similar for carbon dioxide, because carbon dioxide can be produced by volcanoes, and methane can be produced by many other physical processes. So I don't think anyone in the field really has an idea that is going to convince everyone else in the field. There are certain priors on various different biosignatures, but I don't think we have a quorum on basically what will count as a biosignature, leave alone their actual measurement. For the measurement, we are starting to make progress. Again, as we go to cool stars, we are able to get higher amplitude for these spectral features I just showed, and that allows us to at least search for such signatures, interpreting them and contextualizing it in the context of life. That is, I think, a decades-long journey. We are just starting.
I'm fascinated by the shadow snap phenomenon right before or at the beginning of the solar totality, and I couldn't find any good explanation on the internet.
The shadows.
Is there any good hypothesis about what happened?
Yeah. So that's actually because so you know stars twinkle, so it's basically the same reason. So if you look up at the night sky, for example, planets don't twinkle because they're extended objects, whereas stars are point objects, so they twinkle because of atmospheric scintillation. So the index of refraction actually space and time dependent, and that's basically causing the stars to twinkle, photons having come from the same, roughly, approximately point source. Now, for the solar eclipse, same thing, because I just had a picture of that. Let me just put that on. So as the lunar disk is occulting the solar disk, well, first of all, you know, moon has a very rugged surface. So it has these, mountains and valleys. So because of the valleys, as the moon completely occults the solar disk, there will be a few points where light will remain until the very last few seconds. And those will go away one by one. They're called Bailey's beats, I think. Historically, they were characterized centuries ago through careful observations. But the very last remaining one will eventually behave like a point source, like a star. And that's actually going to cause time variable in brightness in that very last amount of light that's remaining, and then it will go away. So as you watch the solar eclipse from a given point on Earth, you will actually see this luminosity basically go up and down, and that fluctuation is going to increase up until it will become zero.
How much data are you getting from tests? How many megabytes a second, terabytes a day? Where is that?
So we basically have 16 CCDs, 4 cameras, 4 CCDs in each. And we are using the deep space network, DSN, to basically downlink the data, and that's not always available. So the average, I can't remember, but it's in the order of a few tens of megabits per second if you average it. So the actual instantaneous can depend on many different factors, and it's not a priori known. We more recently started getting 2 contacts per orbit. So when the mission was launched, it was actually receiving 1 contact per orbit, which meant that during perigee, we would actually use the network to downlink all the data. And in the rest of the orbits, the test mission would continue observing. Now, instead of doing that, we establish another contact at apogee that is much shorter. So that has changed the amount of data we can downlink. It increased it so that we can actually downlink the entire image, which we call technically full frame image at a higher cadence, at a higher frequency.
How many, some of these drops?
Sorry.
How many pixels in your CCDs?
Our CCDs are 2000 by 2000, so small.
It's a lot of data, so you gotta look at every star over time and see if it's changing, and what rate are you looking, a few times a second, or because you said the transits are hours?
Yeah, transits are, well, around main sequence stars, yes, about hours. If it's a white dwarf, could be minutes, but yeah, so usually we bin the data. TESS is shutterless operation, by the way. There's no shutter, but the underlying exposure time is roughly 2 seconds. So we bin it up to get basically a cadence at the shortest end. We have a spectrum of cadences available. At the shortest end, we offer 20 seconds. And at the longest, we used to offer 30 minutes. Now it's down to 10 minutes. Sorry.
Some of these drops in luminosity, are they always planets, or could they be comets or asteroid clouds that will pose a different drop in luminosity? So you have other transients that you can find in the sky.
Great. So these are called stellar occultations, and they are a thing. They do happen in nature, but they are much more rare than transiting planets. So transiting planets are relatively more common because these are close-in planets. They're very close to their stars, so they happen very regularly. Now, if the occulter is in our solar system as opposed to a close-in star that is, close-in planet that is orbiting that star, that faraway star, then the occurrence rates, first of all, are completely dependent on what object in the solar system we are talking about and how small it is. Now, with the comets, there are certain cases where comets have been tracked to actually cross distant stars, and that has allowed solar system scientists, unlike me, to figure out and characterize their atmospheres and exospheres. That is possible, but the occurrence rates kind of depend on the context.
Are they finding planets on all categories of stars? For one, and number 2, are they studying people using this information?
So what's the second question?
The study people using this information.
Oh, SETI, yes. So SETI people certainly do make use of these time series data to search for interesting occulters. And I'm interested in that problem as well, but so far we have not found any convincing, interesting occulter, although there has been a few cases where the transit periods really look weird. There are some random repeaters that I think require some further investigation. Regarding your first question as to whether all stellar types have planets, in general, the occurrence rate of planets should probably be low for very high mass stars because there's probably not enough time for these planets to form. because they may be super young. We are talking about like a few million years old. But there's certainly no ground rule to say that they should not exist. We can always be surprised. And on the other end, for evolved stars, it is somewhat likely that those stars eventually lose their planetary content because they lose mass. As they do so, they disturb the orbits of the planets around them. In particular, because their total mass, the total mass of the system is changing, the planets can cross resonances, and that can excite eccentricities, and that can eventually make the system dynamically unstable. That will cause certain planets to rain down onto the star and other planets to be ejected from the system.
So mostly you're seeing planets that are close to their stars, like closer in than Mercury is in our solar system.
Usually, but not always. Yes, usually.
Because those are the ones that go fairly often.
Yes.
That you can pick them up. If it's like our Jupiter, which takes a couple hundred years to go around our sun. If you're looking from outside, you're going to see it once every few hundred years. You're not going to, if you miss that, it's a couple hundred years, you see the next time.
Yeah. Well, Jupiter's 12 years, so
Okay.
you know, a couple of tens of years, but there are certainly cases where we can find transits, repeating in fact transits, at orbital periods much longer than 88 days, which is Mercury. We can do like Earth's orbital period and even beyond that.
So what is the calculation of how many planets there are? I understand that almost every star has planets. That's the so there are trillions of stars, universe, and there are trillions or hundreds of trillions of planets of universe.
Right, so we certainly don't know exactly how many because, again, many planets might be too small to be detected in transit methods. So in transit methods, our surveys are completely completely incomplete, fairly incomplete. There's a small radius end, so we really don't have any idea. But for those that are large enough for our complete or for our transit surveys to be complete, we do have a rough idea, and for that we usually quote like a few per star for the larger ones. For the smaller ones, we just don't know. But for the larger ones, a few per star, which basically makes our stellar system kind of typical, but only in that sense. Thank you. Only in that sense. So in general, it's hard to say something very comprehensive based on the current survey. I see people leaving, but maybe let's do like a formal conclusion. So whoever wants to leave can leave, but I will be here for any questions moving forward. So thanks for that. Thanks.
Thank you.
Yeah, please take one glass if you like,
Thank you, very good. Excellent.
Thank you.
Oh, what was the course?
Planets and life in the universe. It was in the fall. Cross-listed to grads as well. Thanks. Okay, so because it's very small, so that means roughly all photons are coming from the same point.
Okay.
So that point, as it enters the atmosphere, it will first encounter a particular index of refraction. But that index of refraction is going to change over time at a very fast, rapid way because of turbulence.
Okay.
And that's going to, yes, because of air, because of atmosphere. Yes.
Thank you.
One question. Can test determine